Good afternoon, everyone. I am happy to welcome you all in the 5-day faculty development program on algebraic structures organized by Research Department of Mathematics, Nesamani Memorial Christian College, Martanda. Today, we are getting into our third day program. First of all, I like to invite Dr. D. Nida, Assistant Professor, Research Department of Mathematics, Nesamani Memorial Christian College, Martanda, to deliver the welcome address and to introduce our today's resource person.
Good morning to everyone. It gives me an immense pleasure to welcome all the participants and resource persons to this faculty development program on algebraic structure. On behalf of Research Department of Mathematics, NMCC, I extend a warm welcome to our resource person, Dr. S. Anantharaman, joined us today to share their valuable insights and knowledge. Your presence truly enriches this program, sir. Next, I would like to welcome our HOD, Dr. A. Pramila Inbaros, who has been the backbone of this event. Next, I would like to welcome all the faculty members and research scholars who have taken the time to be a part of this program. Welcome you all. Once again, I extend my heartfelt gratitude to the resource person, organizers, and participants for being a part of this event. Now, I would like to take a moment to introduce our resource person for today's session, Dr. S. Anantharaman. Sir completed his UG degree from University of Madras and PG from Annamalai University. Sir completed his PhD in mathematics from Annamalai University. Sir has 11 years of teaching experience. Sir has numerous research publications in reputed international journals. As an administrator, Sir has held several key positions. He organized many programs, including National Workshop on Graph Theory, FDP on software tools using mathematical computation. Sir delivered invited talks at various institutions. On behalf of everyone gathered here, I welcome you, sir. Now, I hand over the session to Dr. S. Anantharaman. Over to you, sir. Sir.
Oh, okay, ma'am. Thank you, ma'am. So audible, ma'am? Ma'am? Ma'am, are you audible?
Yes, sir, you are audible.
Oh, okay, ma'am. Thank you, ma'am. First of all, I would like to thanks to the principal ma'am and Christian Management Memorial College of Management and HOD of the Mathematics Department and convener Neveda ma'am, and then organizing committee members. And one more thing, sir, they will be sharing only for that. Just the one kind of the motivation will be present here for the not for entire things. And so my main things are there will be concept will be interested and seeing of one of things they will be do the this kind of research. Okay, and I will share the PPT once again. Ma'am, are you visible?
Yes, sir, it's visible.
Visible. The PPTs are visible. Okay. Today my topic is algebraic structure associated with the graph. And already the Meda ma'am introduced myself, and I now go for the next step. And outline of my talk: introduction and geodesic graph and twin edge coloring of a graph. For not for that entire things. Just I will do for one of the algebraic structure in our things they will prove for here. And most of things and many areas are available. They will be not for the mathematics students, the mathematics thing. They will be computer science also, they will do work in the same area. And many of things are available. They including that and Laplacian matrix and Algebraic graph and Morphoid and so many things are available. So here I will do only two things are one is an zero divisor graph and second thing is twin edge coloring. Introductions. In this lecture, to be a basic idea about the concern with the uses of algebraic technique in study of graph. We aim to translate the property of graph into the algebraic property and then using the result and method of algebra to deduce the theorem about the graph. Okay. And already the many of the classes, first year classes are will be introduced one of the basic definition in algebra group and Abelian group and cycle group and ring and commutative ring and zero divisor graph. Because of I remember this is one of things I need the here the one or two explanation I need the basic definition for the algebra. Okay, I hope that all of you the basic idea basic of the definition already I know many of them. So no one explain here. And next the same thing for the basic definition in graph theory and graph, path graph, and cycle graph, and complete graph, bipartite graph, diameter of the graph, maximum degree of a graph, vector coloring of your graph, and edge coloring of a graph, and girth of the graph are matching are one factor. Because of I here using that above things. So hope and I hope all of you the above two things and algebra and graph theory, the basic definition already known. Anybody ask the question about that about two definition? Because of if you explain the inside the theorem, they need the above basic definition. Anyone? Suppose anyone need a definition of the above two things? Okay, I hope all of the known, very well known. And the algebraic graph, yeah, graph constructed from the algebraic structure, such as group, ring, or etc. So many things. So they will, including the set series, will be considered for the matroid. And the first of all, that coloring source coming introduced the zero divisor graph, and then something sir 1988 coloring commutative ring. The first purpose of the Euro divisor, only for Euro divisor. Previously, so many papers are available, but I have only for the first paper in Euro divisor graph, the coloring the commutative ring. I mentioned the one or two things are here for so many papers, and recently many ideas are included in the algebraic structure. If you are included, first I feel collected only few things are here. So your front of these and prime and Lucidas are introduced in 1999 prime graph component of finite almost simple group. And 2003 Andrews are here that they introduced the zero divisor graph and Aldous 2006 and non-commutating group of graph of proof and although they will introduce the 2007 non-cyclic graph of proof and 2013 the cycle graph of finite proof and meta all 2014 co-prime graph and Regendral and 2016 they are order prime graph. So it is one of the minimum things. Just you are motivate, they will be developing chain. How to develop the again the four way in the research. Just only for that. And next I go to my topic, this zero divisor graph. Already known that in algebra, they agree what is the zero divisor, where the multiplication will be given as 0. So they will be change that here, okay, in graph. Here, zero divisor graph is a graph of ring or where the vertices R and S are connected. The vertices R and S are connected if all that S equal to 0. The multiplication is 0. There will be the elements are came from the ring, the modulo, okay, and then give the values. And next say, and vertices value. And next say, there will be 1988. That is 1988. Beck, the first of all introducing the graph, and they mentioned the Beck graph, designing a vertex for each zero divisor of a ring. But the structure of the graph are not very interesting because of all the zero elements they will be multiplied getting the zeros. So they will be incident to all the vertices, so they will be put a zero in the graph, they will be incident to the others. So it is not interesting. So go for the, it will be more things. And next day, they will introduce to Anderson in 1999. We can see the remove these the above graph for zero devices. They will getting the special structure. They will study the many of the properties in our graph. Okay, and one of the example for zero divisor graph I given. Okay, and Z of 3, the elements are 0, 1, 2 only. There is a Cartesian product of Z3 and Z3. They will be the elements are 0 0 and 1 comma 0 and 0 comma 1 and 1 1 and 2 comma 0 and 0 comma 2 and 2 comma 2 and 2 comma 1 and 1 comma 2. It is an elements they will be constructed from Z3 Cartesian product of Z3. They will be, and next they will draw the above things in algebra to the graph. First of all, they will multiplication will be get the zero element 0 0. So the first element they will be multiplied 0 and 0 for getting the 0. So they will be connected to the 0 to 1 to 1 comma 0. They will connected to edges. Okay, and again 1 comma 0 and 0 comma 2 to the 0 and 0. So will be I connected to the above two things in our edges. Okay, and we will connect it. And then next 0 comma 2 and 2 comma 0 they will be getting the values for 0 comma 0. So I will connect it to the above things. And finally they will be connected to 2 comma 0 and 0 comma 1 and connected to because of their result will be 0. So here the one of the example for he will be study for the algebra. They will be translated to the graph vertices and edges. They will be translated to the here. Okay, and next is the one of the additional example for more interesting that because of that here uh, one more thing x square xy and y square is a 0 sir. So they will be normally they will getting the basic elements of rings and 0 1 x y x plus 1 y plus 1 x plus y and x plus y plus 1 they will getting that. So here they only for we take x y x plus y because of that will be give for the only for zeros. They will x y equal the model of 0, so they multiply they will be x y, and again we will multiply x in they will connect x into x plus y. They will multiply to the x square plus xy. There will be x square is equal to 0. So now xy is 0. So the modulus are available. They will be getting the zeros. They will be explained here. And next one more thing, they will be explained x plus y into y. They will be again, they will be connected. So I will connect the graph x, y, and x plus y. So we can multiply and getting the graph. Okay. And any question from the above example? Because of that, you know the algebra to the graph theory. So you're getting the idea. That next I will explain the theorem. You will understand. Okay. Any questions about the example? Are you understood that the algebra to the graph theory they will be converted? How to convert that? Because of the zero device. Only I think here I explain only for zero devices. Okay. Okay. So no questions. So go to and next I go to the sum of the graph, the beautiful graph. There is for only for that, only isolated and path of length 2 and path of length 3, tricycle and star graph and C4 graph. Only so many things are available. Okay, they will be one of things. They will be getting the structure. The structure they will be explained that. Okay, and next I go for the one of the theorem and 1999 and all. They will explain that one of thing let R be a commutative ring. Then gamma of R is connected with the diameter of R less than or equal to 3. So here I using that there will be commutative R is an commutative ring and gamma of R means that the zero divisor graph. Gamma of R is an zero divisor graph. And almost one more thing, sir, you know that diameter of the gamma divisor graph. Okay, diameter means that there is an path form from the longest path from the graph. Okay, there is a longest path, so it will be 3. Okay, so longest path is will be 3. Okay, and then we have proof for the one very interesting proof of here, and let x comma y in instead of or be a distinct elements. I take two elements. We shall show that diameter of x comma y is less than or equal to 3. Distance. There will be distance. D means the distance of x comma y less than or equal to 3. If xy equal to 0, then distance will be 1 because of the edges will be connected, directly connected to x to y. So distance no. So distance of x comma y is on 1 edges between the above x and y. So it's on 1. Suppose that x is a non-zero, x in y is a non-zero. That is means it's not equal to 0. Then there exists a element z comma w in z of y such that and sw sz is and wz will be getting the zeros. They will be connected. They will be connected. They will be connected to the graph. Okay, they are existing. Definitely, there will be elements are existing. Okay, and so suppose if and zw is equal to 0, is not equal to 0, then there exists a path x2 is w and y is a path of length 2. Is a path of length 2. So distance is d of x comma y is an 2. And if z of w is equal to 0, then there exists a path x to z and z to w and w to y is a path of length almost 2, 3. We could have a x equal to z or w equal to y. Okay, and thus finally there will be distance almost d of x comma y is an 3 only. So hence the gamma or some zero divisor of a graph is a Gaussian diameter less than or equal to 3. Less than or equal to 3. So only for here property will be structure associated the graph. So we will explain that the one of things most interested. Okay, and next, one more thing here. Let R be a commutative ring. Let R be a commutative ring. If R containing a cycle, R containing a cycle, then girth of R less than or equal to 4. Girth of R is a less than or equal to 4. Okay. What is mean by the girth of graph? This is the shortest cycle. It's the shortest cycle of the graph. Okay. So almost the shortest cycle of the length is in 4 only. Okay. And we have to go to the proof and assume by contradiction. Okay, assume by the contradiction. So n of width of R is not equal to 4. This means maybe the 5, 6 or something. Okay, okay, and let the path x x2 dot or sorry, I take the cycles x1 x2 dot dot xn and then complete the x1. So it is an cycle, but length is not no need of this. Maybe 5 or 6 or 7, no problem. Okay, be a cycle of minimum length. I have the cycle of minimum length. So S1, S3 is not equal to 0 because of not connected. X1 after X3 is not connected. So it's not zero divisor. Okay. So it's not equal to 0. If X1, X3 is not equal to X of I for 1 less than or equal to I less than or equal to N. First of all, I assume this one. After that, I will raise. Secondly, I assume for this either or cases. Okay, for maybe the for difficult things, I will take the one more cases or another things. Okay, and x1 x3 is not equal to xi for one less than or equal to I less than or equal to n. Then we can find a cycle s2 s3 s4 s1 s3 and s2 is a four cycle. They form a four cycle. They form a four cycle. Okay, it is a four cycle. It is a contradiction. Because of that, not available for the girth. It's a not four. So, but by getting the one of the cycle will four cycle. It is a contradiction. Thus, if x1 x3 now equal to xi, because of I take not equal to xi, suppose I take equal to xi, and for some one less than or I less than or equal to n, and if x1 x3 equal to x1, x1 x3 equal to x1, then x1 x2 x3 x4 and x1. This is a four cycle. You can form a four cycle. Okay, it's a four cycle. Again, one of the cycles are available. Suppose if x1 x3 is equal to x2, then it is a form a three cycle. It is a form a three cycle. x3 and s2 s3 s4 and s2 is one cycle. Okay, that will be the four cycle. And if x1 x3 and xn, then x1 x3 x4 is an s3 is one of the cycles are available. Okay, and x3 that will be available that three cycle. Okay, and hence x1 x3 not equal to x1 x3 or xn. However, then x1 x2 and x2 x3 and x2 x1 and minus x1 is an four cycle. This will be contradiction. Because of that, I have maximum length is on not for 4, but because I take maybe 5 or 6 or 7, but I will find the new of things will be for 3 cycles and 3 cycles and 4 cycles. It's a contradiction. Because of that, you have to take the cycles. Therefore, maximum length of the cycle is 4. Okay, maximum length of the cycle 4. So they go off for zero divisor of graph having the girth only less than or equal to 4. Maximum length will be 4. Okay. How here in this section we have only for two things of the theorems, and because of those so many theorems or so many filters are available in the zero divisor graph and more than on 100 purpose for publishing, and then more things are here. And then remaining things you need the more knowledge from the understanding, because of that proof will be very very short. The proof will be very very short. That thinking of this, it is a little bit difficult. So just avoiding that the remaining theorems are here. Because of that, understanding is more complicated. So I will take only two theorems for the zero divisor graph for interesting only for that. Okay. And any question from the in this zero divisor graph section? Anybody ask the question? Because of I go for next section for the next topic for twin edge coloring. Any questions? Okay. I hope all of you understand. Thank you. And then next I go to the new topic for twin edge coloring. So here you know very well for edge coloring and vertex coloring, because suppose nobody know that the proper edge coloring here only I consider only for proper edge coloring and proper vertex coloring. Because of the twin edge coloring, somebody are considered for not for the proper edge coloring, only for proper vertex coloring. Here I consider only for that proper edge coloring and proper vertex coloring. Also I have considered here. Okay. And here the introducing the Jones and Winsong for 2014. Okay. Let K greater than or equal to be a integer for a connected graph G of order at least 3. Let C into E of G to the integer modulo K.
Sir, 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 you are not audible, sir.
Okay, it is considered only for proper H coloring. Are you audible? Any questions?
No, sir, no.
Okay, ma'am. Okay, thank you. And next, we introducing the vertex coloring here. V of G into Z of K. Ma'am, this is one of things. They will same twin edge colorings are possible. There will be improper twin edge colorings are available. They will consider for not for proper edge coloring. They will be only consider proper vertex coloring only. But here, the first I introduced that here both the things. One is a proper edge coloring. It's also a proper vertex coloring. Okay. Okay, and it's defined by sigma of C equal to that means the incident edges the colors will be added. Okay, in instead of P, where is of G is a set of edges is of G incident with the vertex P, and the sum of indicated phi here instead of K. Okay, and then instead of proper edge coloring. Okay, there will be minimum numbers called the twin chromatic index. Okay, and anybody having the doubt from the above definitions? Here consider one is the elements, the colors are collection from the Z of K. So integer modulo K. Okay. And then it's a proper edge coloring. And then they will sum all the edges of the colors. They will give the vertices colors. There is also the proper. They will consider two proper edges and vertices. Okay. I hope all of you understand the definitions. So any question you can ask me. Okay. I go to the next. So I have I have the twin edge 4 coloring for the Peterson graph. Twin edge 4 coloring for the Peterson graph. Then here and almost the Peterson graph having the vertex coloring and edge coloring to be various. But here one more things are maybe the vertex coloring, the edge colorings are 3, and here sorry the 3. I here will be 4. Definitely they will be having the first I have first of all I put the colors in edges 0 1 something. So next they will be ordered here, and 0 1 plus 2 they will be ordered, they getting the result 3. Suppose here I ordered the color the instance the color 3 and the colors incident to the 0 and 1. You can add the 4, they will be modulo will be 0. So we can take color 0, 1, 2 only. 0, 1, 2, 3 only. Okay. That will be give the things. Okay. So next is since a 2-in-H coloring is not only proper edge coloring, so there will be 2-in-H coloring always the maximum of the vectors coloring and edge coloring. The maximum of the vectors coloring and edge coloring. And next. Here, Anderson, Andrews have proved that any graph, for any graph, order at least 3, then there exists a 2-in-H coloring. Although maximum bound is 2 power m minus 1. Maximum is 2 power m minus 1. Here, all the proof technique will be using the one factorization. So maybe they're using the one factorization. Okay. They will be color the one factor, they will be collect the matching or one factorization. The color matching the give the same color. You collect the another matching, they will give the another one more color. They will be using the matching coloring will be here. Okay. They will be set of matching. You collect the first of all set of matching and then give the color. Okay. Here Anderson prove the maximum 2-in-H coloring is on 2 power m minus 1. Okay. Let G be a graph of size m greater than or equal to 2 if m equal to 2. Okay. Here order 3 for minimum vertices 3 and size m. Size m means the number of edges size m. Here I fix order, so more than 3 vertices. Okay. And then here in here edges are variation because of why I hope that minimum order minimum 3 because of not existing and one vertices and two vertices because of the single edges are available. So they will be not possible for below of 3. Okay. And next I will prove for the here maximum bound if m equal to 2 then assign the color 1 and 3 in instead of 3 to the edges of G. If m greater than or equal to, so if I assign the colors because of m equal to 2 and because of only for two edges. So two edges, they will be put the values 1 and 3, 2 in every places. They will add up, they getting the values for 0, 0, 0, one of things. Okay, the vertex coloring. So they will consider instant edges, they will be receive the colors 1 and 2. The vertices are receive the colors for 0 in instead of 3 to be the edges of G. If m greater than or equal to 3, then assign the m elements, m greater than or equal to 3, then they assign the m elements 0, 1, 2, 3, 2 power m minus 1 in my integer modulo 2m minus 1 to the m edges of G in a one-to-one manner. One-to-one manner, they will be they particularly that matching or one factor. They will one-to-one manner, they will be given. So that the colors zeros assigned to the pendant edges. If possible, they will be available in pendant edges. You can put the value for 0. Value is for 0. Otherwise, no need of the put the value for 0. Okay. If G has such edges, hence the set of edges colored by the non-zero element is set of 2 4 n minus is set of integer model of 2m minus 1 that are incident every two adjacent vertices are distinct. So will be the sum will be definitely they will be different. Okay, there will be some will be definitely different because of that no zero elements are included. So will be added the different position and different things. Okay, maybe the vertices are receiving the 0. It's possible, but then as the adjacents are different. Okay, in since the basis to representation of the colors of these vertices are different, it follows that adjacent edges are different colors. That's the 2-in-H coloring. So I have colored the any graph, they will color collection, they will complete all the edges, and then there will be some of the vertices colors are different. So I enough for the any graph, they will be 2-in-H coloring colors are 2 power m minus 1. Okay. And here, one of things, path will be received 3 and complete graph of n. If suppose n is uneven, there will be n plus 1. It's already proof for the Andrews. That is a proof, already proof. There will be result will be already proof. The because of I here one of two things are here mentioned here for the I make the complete and complete biparty graph to the and given by the theorem, they will be corollary to the others. Okay, because of they will do the one kind of proof. They will be two for in the additional things they will be getting corollary. Okay, that is one of things I take here. Otherwise, no needed. Okay, and the and C and C of the only one cases are C5 having the teenage coloring will be 5. This is the most worst cases are here. The only one graph. Okay, it is one of this. Because of that, maximum degrees and cycles is 2. Because of the 2, I need the more than colors, 3 colors. So it is one of the worst cases are C5. And complete bipartite graph A, comma B, that is condition that, and complete graph of the same bipartite A and B, they will be A plus 2, and then one thing are A or A plus 1, no problem. That is will be A plus 2, and yeah, 1 comma B is an, and then B plus 1, and 1 comma B is an B plus 2 if you modulo 4 and modulo. It's on a modulo 4 and it's not modulo 4. Okay, here explain that any connected graph, there will be need one more thing for the upper bound 4 into delta of G minus 3. Okay, it is a proof will be lengthy. The proof available that Johnson and there in our this is available that proof. Because of that, even not including the maybe the proof maybe take more timing. So I will skip that. You are known for the upper bound not for this. Upper bound is not for this. Now I have upper bound for the 4 delta of G minus 3. So delta of G is on maximum degree of a graph. So there will be how the one more upper bound for the and Johnson's. They will be necessary to prove one of things proof. Okay. And next, one of the observation I given that, and most of things the groups of edge coloring, they will prove that the delta and delta plus 1. The colors are edges are colored only for maximum degree. Enough. The proofs are already declaring the proof to that. Here, I explained that here most of the graphs may be the possible to a 1 plus delta of G. If a connected graph, G contains two adjacent vertices of degree delta of G, then high D dash of G greater than or equal to 1 plus delta of G. And this is a observation they explain here. You can collect the neighbors of U and V. So adjacent vertices or neighbors. If E1 and F1 they connected, they will be participate to the neighbor of N of E1 and N of E the same color. And then sigma of G and sigma of G, they will be different. So definitely all the colors not possible to the same colors. So you need one more color to the colors that edges. Okay, that is one of things. The sigma c equals sigma v, they will be existing. So at least I need 1 plus delta color. So in these cases, I explained that two adjacent vertices of degree in maximum degree, then definitely he have the lower bound. Definitely you have the lower bound 1 plus delta of G. And basically normal edge coloring, they have the minimum lower bound only for delta of G. Only for minimum discoloring the lower bound is on delta of G. But here, in these cases, I have twin edge coloring. They will be minimum edge coloring 1 plus delta of G. And they posted the conjecture, Andrew sir, that we find the graph, it is not possible. If your graph connected graph of order at least 3, that is not a 5 cycle, then high t dash of G less than or equal to 2 in delta of G. The only worst case they will be explained that in a previous paper, that is Andrews also that 3 plus delta of G. And then we tried to find the other graph here. They will be family of graph, and we will try to disprove the conjecture. Okay, but still not getting that, they will be not getting the result for the disproving the conjecture. But have exact count of the family of the graph 2 plus delta of G, they may 2 plus delta of G is an exact count of the graph. Okay, here one of these, and one of the preposition I will give on for that. And here in the exact count will be exact one will be k plus 2. It is the main things of the problems that they will disprove, they will the conjecture to that is corollary to the complete bipartite graph, because of maybe the complete biparty graph, there will be regular graph. So I try to the previous term for the things. Okay, and let G be a k regular graph of odd order at least k plus 2. At least k plus 2. If for any two non-adjacent vertices u and v, then also that n of neighbor root of u and neighbor root of v is the union equal to the vertices of G is remove that v of u comma v, then they will be the twin chromatic sensors, the lower bound will be k plus 2. The lower bound will be k plus 2. The graph, but the graph is on k regular. So maximum degree k. But here the minimum bound k plus 2. The minimum bound k plus 2. So I will try to the above things will be try to the disprove the conjecture. Okay. And but not for the not disproving, but only for I will try many of things, but no for that. Okay. And to see this, suppose IT dash of G equal to k plus 1, then there exists a twin H k plus 1 covering C of E of G in integer modulo k plus 1. As the G is an k logral for any vertex X, some color psi is not represented for the edges incident at X. Okay, it's an incident not presented for the edges incident at X. Okay, and since there are k plus 1 colors and the cardinality of V of G is greater than k plus 1. Okay, so the colors are we mentioned that by Pigeon hole principle, some colors the I is not present at two vertices. So some colors not present for two vertices. Since sigma c equal for this is two vertices. Okay, they are adjacent. Let the two non-adjacent vertices be U and V. By hypothesis, I must be represent on all the vertices of V of G, U comma V. Okay, this is clearly this most not possible because of V of G is removed from the above two is getting the odd. So definitely here mention the odd order. They will be mentioned the odd order. So it is not possible. So how minimum lower bound is on k plus 2. Okay, and next I will first of all I will introduce the new families, and one more next for the one more family for the graph. They will be degree minimum lower bound is on delta of 6 plus 3. So minimum lower bound. Okay. Any questions? Because one or two theorems are explained. First of all, the lower bound, and then one more thing. So they will be found the for one of the pressure family of the graph. And next we will do the same and then new families. Not for that. Okay. Extra and one more thing. The new family I will explain that here. Any questions for all of you understand? Okay. So no questions. So I will proceed for next. Because of that, I will explain here. But how many members are understand? That is one of things. No need. Okay, thank you. And go for the next theorem. And let k greater than or equal to 4 and let h be a bipartite graph and k minus 2 regular graph of 2k. That is a sixth property that for any two vertices u and v of h, nh of u not equal to nh of v, then it dash of h greater than or equal to k plus delta of h plus 2. Because of here, I take only for regular graph, they will be put the values, they will be, we are trying the first things, if possible to the disprove the conjecture, number one. Number two, here the family of the graph will be constructed from the maximum bone. It's an exact bone. It's a maximum bone. Okay, maybe exact. Okay, they will be find at that. Okay, that is one of things for here. By hypothesis, there is no independent set of I of the vertices H such that I intersection H is equal to 2 and I intersection Y equal to 2. Because of that, here will be mentioned here. Okay. Okay. Next. Proof by the contradiction. Suppose We have assigned the edges of subgraph will be colored to the here and twin edge coloring k minus 1 coloring. Then each VI have exactly one color is not represented at the edges incident at VI. Okay. Only then every edges, sorry, every vertex exactly one color are missing. By the pigeon hole principle, there is at least three vertices and some colors say Ci such that Ci is not represented at this is three vertices. So Ci is represented at three vertices. Okay, and if all the three vertices are in the one portrait set, if all the three vertices are in the one portrait set, say X, then Ci may be represented at most k minus 3 vertices of X, and therefore Ci may be represented at most k minus 3 vertices of other coordinate set Y. So how two coordinate set X and Y? There will be one coordinate set available in Ci, other coordinate set not available in Ci. That the above mentioned the missing three colors. So we have three vertices in X and three vertices in Y such that Ci is not represented at this is six vertices. Okay, as we go to for the vertex coloring, as sigma c is the same for this is six vertices, they form a independent set, they form a independent set because of the previously they will be edges are independent, so will be the colors also they will be form a independent, so it's a contradiction. If of two of this is three vertices are in X and others in Y, then Ci may be represented at most k minus 2 vertices of X. Therefore, Ci may be represented at most k. So we have two vertices in X and two vertices in Y such that Ci is not represented as this is four vertices. So sigma is same for this is four vertices. They form a independent set. It is a contradiction. Okay, it is a contradiction. So finally that maximum degree, the minimum degree is on delta of h plus 2. Okay, that's a k. Next, we have form a new subfamily for previous theorem. Okay, and next we establish the subfamily of the above knee family with id dash of g is an delta plus 2. Because of here, I mentioned that this an bound will be minimum bound will be delta of h plus 2. Okay, it's a minimum bound. Here mentioned that the subfamily will be the exact form delta plus 2, exact form for delta plus 2 because of still no idea from the exact coloring, but maybe the variation they will go through for the above families, they will go through for the new things maybe possible to the disprove the conjecture will be constructed doing the work research work. Okay, and here but here is an exact point, it's an exact point of the graph. There will be subgraph, subfamily of the above graph. Here I use the coloring for the two factorization technique. Two factorization technique. You have using here and the color the all the edges. There will be possible all the twin edge coloring of this. And let k greater than or equal to 4 and let h be a bipartite k minus 2 regular graph on 2k vertices with the property that for any two vertices u and v of h, the neighbors are different. The neighbor sets are different. If H contain a two factor, H contain a two factor, and F such that each component of F has a zero mod H edges, then they will be getting the upper bound for the exact bound for the delta H plus 2. Here, oh, so many conditions are available. The graph is generally the graph is an one of things, and there will be two k vertices, and neighbors are the two vertices of the neighbor are different, and have H having a two factor, and one more thing, the factor will be 0 modulo 4. So how more than three conditions that will be included, and then they will be getting the exact form. But previous theorem, there will be lower bound I given for not exact. Okay, just like finding that exact form, they will be need the this is kind of the conditions. Okay, next. By previous theorem, I dash of h is greater than or equal to k because of I already proved. Let x comma v a bipartition of a h because of that k they given that 2k 2k. So they will be partition the two things, x and y, be a partition of the H. By hypothesis, H minus EF is a bipartite graph and K minus 4 regular graph, and so it is an one factorable because of one partition and one more partition. So neither one then, and say H minus E of S is an, here mentioned that is a one factor of module, okay, where Fi is an one factor of, and H minus F is a edge disjoint unit. They did above every F1, F2, F is an edge disjoint. Edge disjoint means they will be, it is an different things. Okay, so edge disjoint union define C of E of H to the integer model of O. Now they give the colors to the edges in integer model of O as follows: 1, 2, 3, K minus 4 color. Okay, the edges Fi in I plus 3. So next is the colors edges of F with the 0, 1, 2, 3. If C of E, so they will be mentioned the colors in the component of F, where it is a component from the X and it is a component from the Y. Then we color the edges of C of 2P as follows by assumption P is an even. P is an even. Okay. Here then define the colors 0, 1, 2, 3 and 0. The colors are defined. Okay. Observe that the every colors will be 3, 4 plus and modulo K, and again is an X side and the X portrait set, and next is an Y portrait set. There will be 1 plus 4 plus 5 plus 6 element for that, because of our 5 plus 4 plus 6, because of that elements not available, they one or two things elements are not available, then will be definitely there will be vertex coloring sigma c is different. So it is one of the possible things, because of there will be not available the some colors are here also not available, so definitely above two things are different. So sigma of c of x is not equal to sigma of c of y. Thus C is an 2 in each coloring of H. C is an 2 in each coloring of H. Okay. And any question? Audience, learners, friends, any questions? I have explained two theorems. One is a general bond. So minimum bond is a delta H plus 2. And next I will give the exact bond. And so many conditions. Three conditions are equal. They will getting the exact bond. So no patterns are available. Only they will be having the only one pattern. It is possible one factor is will be give the colors of things. Okay, because of the mob, they will be edge colors disturb to the vertex color, because of the sum of the edge colors will be give the vertices. So no patterns are, it's immediately not possible. So that is one of things. Okay, I hope all of you understand. Okay, next next section here that we found that so many colors of this here. Okay, sorry, so many graph family of the graph, the colors will be 2 plus delta of G, 2 plus delta of G. Okay, Cn, so n greater than is not equal to 5 and n equal to 5, there will be model of 5. The colors will be delta of G plus 2, and Kn complete graph of E1, then n greater than or equal to 4. It is the colors of 2 into delta of G, maximum degree plus 2. And next, the modulo 4, the pi party graph 1 comma p, and the modulo 4, b values modulo 1, modulo 4. They will be getting that colors are delta of the maximum degree plus 2. And complete pi party graph of k a comma a, there will be partition that will be same, a greater than or equal, so will be the colors will be same, maximum degree plus 2. And tree t plus d is a regular order of the at least 6, and delta of 1 minus 4. And then one of things c5 partition partition of product of k2 and c7 whole square, and complete graph of k9 minus e of g, that is the all the graph will be equal exact values maximum degree plus 2. It is an exact one. But in the conclusion we strongly feel that there is, it is possible to the maximum colors 2 plus delta, it's an maximum is not possible. That is one of things I mentioned here. Okay. Okay, and almost I completed two things. One of the zero divisor graph, and one more thing, sir, 2 in each color graph. it's almost completed. And here only for including only general family of the graph, not for the any simple things. And one more things, they will be general family of the graph. They will be find the lower bound, upper bound. So you need that exact bound. So many conditions are needed because of the family will be finding that this more difficult. Okay, that is one of things. Okay, and finally we conclude that is possible, but this is possible to disprove the conjecture, but we will try more. Okay, in the twin edge coloring and zero divisor graph, more of the more of the concept are introducing. That is a zero divisor graph, one of the interesting factor previous to here. Okay, just I to here explain one of things. Okay, so only for interesting factors of zero divisor graph. Okay, and here second things they same, but we will try more for the graph families of displaying the conjecture. Not only this, is on more things of available in the algebraic structure associated with the graph. Okay, and almost completed the section. I have using the reference for the above things. The first one of the twin edge coloring, the introduce the concept, and next one the zero divisor graph, the coloring of the commutative ring. The first of all introducing the zero divisor graph, and remaining things are almost the books. Okay, almost the books and nothing. Okay, any questions? Okay, thank you, ma'am.
Thank you, sir. Thank you for your nice presentation, sir.
Okay, ma'am.
Participants, it's time for questions. If you have any doubts, you can unmute your audio and clarify now. Otherwise, you can comment on the comment box also. Audience, if you have any doubts, you can ask now. I guess there is no doubt. So we come to the last section of our program. So now I invite Dr. A. Premla Inbaros, Associate Professor and Head, Research Department of Mathematics, Nesamani Memorial Christian College, Marthandam, to deliver the vote of thanks.
Most respected speaker of the faculty development program, respected participants of the program, good evening to you all. Our professor has done a very nice job of traveling between algebraic properties and graph properties. Respected sir, your explanation is excellent. We feel very comfortable in understanding the different structures of graphs and algebra. With immense pleasure and gratitude, I extend a heartfelt thanks to you, sir. A warm thanks to all the participants who are all actively participating in the program and enjoying the session. Thank you, one and all. Have a nice time.
Okay, ma'am. Thank you, ma'am.
Okay, sir.
Thank you, ma'am. Participants, feedback link is sent it through the comment section. So all are asked to fill the feedback before leaving. Thank you.